Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max, Experiments at Large is all about light. And bending light to your will. Right? And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large. Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, turn back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Ann.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're going to challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is going to be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay. Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm going to challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right? Mm-hmm. So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Did you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would... I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation! A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution. Check it out, it's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right. I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light, shine it on the ball so that it's a little bit better illuminated, and then sit in the chair and ask Anne to move it so it's aligned. All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2.
I've got another ball.
Okay.
With something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right, I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope. Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface. And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons. Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then, get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your two mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like. The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television. Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television when you leave the room. I solved Anne's first light challenge, seeing something far away, with a lens. It says 71! But now she's moved the ball around a corner, and now I have the solution. Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay, go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally. Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science. Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Oh,
Anne?
Oh,
Anne?
careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do
No. Hold on.
here.
Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, I'll hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong. Ha ha! Bam! Huh? That is an X-ray, a picture we can take using this part of the spectrum. We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. You got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared. For those of you keeping score, that's this part of the spectrum right here. Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now.
Hey, Sal.
Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here. Oh, right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it.
Okay, here we go.
Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
These are night vision goggles. They use some of they use some things that I cannot pronounce.
Have this container of water. Whoa! And I make it stream. But instead of going straight back, they're going.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha. There are two. Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate me. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Oh, look at that. You could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
And we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets,
everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science!
Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan. Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go.
You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science. So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy. And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, no. Maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get a new camera. Today, we're gonna be looking at the power of magnets. 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 Wait, okay. This one here is called a neodymium magnet, or a rare earth magnet. It sticks to this magnet. Magnet. Ramona, the fish fell. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about liquids. What makes something float or not float?
Oh no! My loonies!
Liquid density and super absorbent gel.
Who wants to do an experiment with diapers?
Liquids. Today on Science Max, experiments at large.
Hey, welcome to Science Max Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? Oh, right. Let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait. That wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Who's Nia?
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Husnia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Here. Where? Here it is. The tinfoil boat. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin, and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil?
Tinfoil?
Okay, high five. I will, I'll take the tinfoil, and you take that, and I'm gonna have to dry off at some point.
Whoa!
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it?
There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo.
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
What should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test. Does it float on its own? Yeah! Floats on its own. No problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my! Bill, are you okay?
Wait a minute. It's sort of. No, that's just air. You know what went wrong? It wasn't boat shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what. Let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it will sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swubby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference.
Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat. So this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
No.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out.
Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to.
Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it. This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No, go. No. No. 2, 3, go!
Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water.
I don't know if fixing it is in the cards. I think we're gonna have to build another boat. So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I'll get it. I'll get it.
Sure.
Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are 2 things you need to remember. First, ask an adult if you can use the diapers for your experiment. And 2, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. What it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
let's do this.
1, 2, 3, lift. All right, let me get over. it floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly. The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Lucia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. I think we should go. I think you and I should just get wet right now. Just need.
Someone help.
You're still dry, aren't you?
Okay.
That is so unfair.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Science! I don't know what you're saying. I don't speak treasure chest.
The one thing I'm really trying not to think about is that this is the stuff that's in diapers.
Let me talk to your brother. Whoa, 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 whoa. Don't talk with your mouth full.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max!
Put on your helmets for this episode of Science Max. We try to build a human-sized cart powered by inertia, plus Newton's laws from a caveman to crockery. Inertia on Science Max, Experiments at Large. Greetings, race fans and Science Maximites. I am Phil McCordick, and this is Science Max, Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is that I don't have to push it, it goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own Dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard.
So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then, cut out your wheels. Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then, add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short.
If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now the last part is wrap some string around the back axle so you can pull and the wheels will spin. Let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient. Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for. Remember how I said an object at rest tends to stay at rest, and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction, either get it moving or make it stop. That is called inertia. It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training. I thought it was bigger. Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And...
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
Of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And
looks like
oh, look, I've got some wheels.
Perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Oh, it's okay.
So, yeah, we build our frame out of wood,
Yeah,
attach the tires on, and then find a way to get them spinning.
and if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground, like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready?
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, try one.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels. and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill?
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question. Should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
Yes.
All right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah! Power tools! Woo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There we go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready?
Ready.
And... Well,
What happened?
so you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the dragster, because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires. Oh, what, on this?
No, I think we're gonna have to build something bigger.
So so we build a whole new frame.
Yep.
What if we got like the axle of like the back axle of a car or something?
It's a great
The
idea.
back axle of a car, and then what we use the drill
I don't think the drill's gonna be enough.
to move the. Why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving the back axle of a car?
Well, I mean a car, but we would have to take it off the car, so.
We could use another car.
We could use another, we could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
Yeah.
back our big dragster.
Newton's laws in 60 seconds.
Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves or doesn't move. I will demonstrate using myself. Newton's first law: an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. Ugh. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass or its weight times its acceleration or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law: object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law: for every action there's an equal and opposite reaction. Newton's second, Newton's 3 laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was.
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force. Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it? No. Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock. That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work.
What?
Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II. This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one. Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up. The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right? Yep. All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul?
Ready.
Fire it up. Go, go, go. Faster, faster, faster.
Keep
Faster,
going.
faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice. It's pretty good. Yeah, that worked. All right, I think, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it. Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step. Me, riding it to glory!
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way. Whoa. All the way. 3, 2, 1, go! Woo!
Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo. Inertia! Whoa. Science! Whoa!
Red bar mark back. Action!
I can't do it. Whoa.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
This episode of Science Max is all about storing energy and releasing it.
Yeah. Let's try it out for real.
Storing it in a giant spool racer, plus a domino chain reaction, mousetrap chain reaction, popsicle popsicle stick chain reaction, and more. All on this episode of Science Max Experiments at Large.
Okay, 3, 2, 1, go!
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. Wow, I really need some more energy. Fortunately, I have some saved up. Ah, that's better. Yeah, I know what you're thinking. Storing energy like that doesn't make a whole lot of sense, but you can store energy, and that's what this episode of Science Max Experiments at Large is all about. In fact, I'm gonna store some energy in this container simply by putting it up here on the top shelf. More on that later. But right now, let's look at another way that you can store energy and release it in a really fun way. We're gonna make a spool racer, and it's pretty simple. Here's all you need. You need some science ribbon. Now, if you don't have science ribbon, you can use regular ribbon, but the ribbon really isn't important. It's the spool that's important.
You'll also need a washer, elastics, pencil or pencil crayon, popsicle or craft stick, and science tape.
Science tape is the same as invisible tape, except I use this one only for science. Here's how you build it.
Break the popsicle stick so it's smaller than the diameter of the spool. Then put the elastics on top of the pencil and pull them tight. Thread the popsicle stick through and feed it all through the hole of the spool. Grab the elastics on the other side and pull out the pencil, and everything will be threaded perfectly. Then stick on the washer and thread the pencil through. Finally, tape the popsicle stick down so it doesn't move.
And if any of these steps are a little too fast, don't worry. All of the instructions are up on the website. That was cool. I can't make it go away. I can only make it come up. So there you go, a spool racer. And here's how it works. You spin the pencil around, and that twists the elastic. Now that elastic is gonna wanna unwind, right? So just keep spinning that pencil around until it's good and tight. And then when you put it on the ground, the pencil's gonna wanna unwind, but it can't because the table's in the way now, which means that the energy is gonna transfer to the spool, which is gonna turn, whoa, and it's gonna drive away. Yeah, let's try it out for real. So why does this work? It works because the elastic is coiled, right? Yes, and because I'm putting in the energy to twist it. You see, I'm putting in effort to spin this pencil crayon around, and then when I've finished, all of my effort has been stored in the elastic. When I let it go, my energy transfers into movement. So that's, that's what we're gonna do today, Science Maximites. We're gonna max out the spool racer. I think Anthony would really know how to help me with this. So, I'm off to the Ontario Science Center. Come on.
Phil! What happened? Phil!
What happened?
You okay?
Anthony.
Yeah, hi.
Oh,
Phil?
were you in the middle of something?
Don't worry about it, yeah.
Oh, okay. Sorry about that. You know what, I was wondering if I could get your help with something.
Sure, yeah.
Yeah, one word. Spool racer. Actually, that's two words. Spool racer. Yeah. You want to help me max out a giant spool racer?
Yeah.
Awesome. Let's go back to Science Max headquarters. Okay, Anthony. Today I want to max out the spool racer.
Awesome.
Right? So you twist up the elastic and it goes from potential energy, all stored, to
Kinetic.
kinetic energy. Whoa. There we go.
Awesome.
So,
Okay.
not too hard to design. Should be fairly easy to max
Yeah, really
out.
simple couple of parts here. We just got elastic band inside.
Yep.
And then this big long pencil to store the energy and then release it.
And the most important part
Is spool.
is the spool.
Exactly.
And I know where we should start.
Where's that?
Right here. This is an industrial cable spool. So the big, thick electrical cables, they come wound on this thing.
Yeah, okay.
So I figure we start with this.
Got it.
And the good news is that it's got a hole already. And check it out, it rolls really well, right?
Uh-huh.
Okay, cool.
Okay.
So, bungee cord?
Yep.
And long pole or something?
Yeah.
And we're ready to go.
I guess let's get some parts.
Okay.
Okay.
Oh, hey, how you doing? You want to buy something? I got a lot of stuff here, and I got a special today only. Potential energy, huh? I will throw in some potential energy with any order. You see this stuff on the shelves here? The stuff on the higher shelves has more potential energy than the stuff on the lower shelves. Don't believe me? Here, hold on. Look at this state-of-the-art traffic controller. Right now, it's sitting up here on this high shelf. Now, if it were to fall, it would be going fast, which means it would have a lot of kinetic energy. You see, when it fell down, it had enough kinetic energy to completely break itself apart. Yeah, well, that's the difference between potential energy and kinetic energy. Look at this bagel, just sitting here, not moving, minding its own business on top of this ramp. It's all potential energy and no kinetic energy. And when it gets to the floor, it's all kinetic energy and no potential energy. Woo! And now it has neither because it's on the floor and it's not moving. 5-second rule. And now you know your energy. So what do you say? You want this thing? Tell you what, I'll give you a discount because you know it's gently used. Hey, I'll even throw in this bagel, huh? Also gently used.
Anthony and I are maxing out the Spool Racer. We start with a long coil of bungee cord, which is kind of like a giant elastic, and feed it through the spool. Then we put on a big piece of plastic to act as our washer and use a long pole as the pencil. We flip the spool on its side to wind it up. Then we flip it back and it's ready to go.
All right, so we have it all wound up and we're ready to try it again, but with one change.
Phil,
Yeah,
what's with the trike?
I ride the trike.
It's like I always say, what's the point of building something big if I can't ride it?
There's no way you're gonna fit on this thing.
No, I don't put my feet on the pedals. I put my feet here on the back, right? And then-
Okay, yeah, I get it. You got it?
Hold on, I gotta do my helmet up.
Safety first. You ready?
I'm on it.
Okay, 3, 2, 1, go.
Oh, it's working.
It's working. Amazing.
All the stored energy in the bungee cord is being released and the spool starts to turn. There's even enough energy that I can get pulled along behind it.
It's not going that fast, though.
No, and
It's pretty good, though. It still pulls me, right?
Yeah, pretty good.
So, Spool Racer, actually able to get pulled by it.
Yeah.
You know what? I think we can go even bigger.
Bigger.
Yes.
Well, what did you have in mind?
I'm glad you asked.
Yeah! What is this?
This is an industrial cable spool, and this is the biggest size that they make. And I thought we would do the same thing with this. What do you think?
I think this could generate a huge amount of energy.
Okay, so all we gotta do is just build it just like we built that other one.
Just bigger.
Except way bigger. Let's do it. When you set a domino on its end, you're giving it potential energy because it can fall. Ooh, and when you put two dominoes together, you can start a chain reaction because that one will fall into that one. But it's a lot more fun with more dominoes.
Setting up a run of dominoes is a lot of fun, but it takes a flat surface and a steady hand. And if you want to do it yourself, add gaps, so if one part falls, it doesn't take out the whole run.
Last one. There. I had some dominoes left, but I did it. I made the Science Max logo. See?
Science
right?
Max!
Sort of. Let's see how it works. Ready? Yeah! Now it's time to max it out. Giant maxed out dominoes! Woohoo! Even though these dominoes are giant, they're still gonna work the same. They're standing up on their ends, which means they've got some potential energy. And when I give this one a push, that potential is gonna turn into kinetic energy, and it's gonna knock the next one, and the next one, and the next one. I hope. I don't know what's gonna happen, but let's find out. You ready? Okay, 3, 2, 1. problem is, when you use dominoes this big, setting them up again is a real chore. This is a mousetrap, but don't worry, no mice are gonna be harmed in the making of this episode. Mousetraps are a great example of stored energy. You see, in order to set a mousetrap, you have to push this bar back, and it's hard to do because this spring holds it. And then you set the mousetrap by putting this little lever underneath this very sensitive trigger, and once you have it set, all that energy is stored as potential energy, but it'll go off with just the slightest touch, releasing the energy. So what if I had a number of mousetraps and they're all set and all of that potential energy is stored up, and I dropped a number of ping pong balls on them? Well, then I could set off a chain reaction where one mousetrap flies and hits another mousetrap that hits a ping pong ball, and then they all go. Now, this is something you can try at home, but do not set the mousetraps yourself. It can really hurt if it snaps on your fingers, so you should probably ask an adult to help you, and then you can see how brave the adults in your house are. Okay, you ready? Here we go. Mousetrap chain reaction. And last one. There we go. And now, let's max this out. Let's do it with 90 mousetraps. And this is a crate of ping pong balls. So, let's see what happens when we put them together. There you go. Maxed out ping pong ball, mousetrap, chain reaction. Awesome.
Ready?
I'm on it.
Anthony and I have built a large spool racer.
Oh, it's working.
It's working.
And it worked so well, the only option was to go bigger.
What is this?
This is an industrial cable spool, and this is the biggest size that they make.
I think this could generate a huge amount of energy.
Building our giant spool racer is the same process as the other builds.
So the steps are exactly the same, but on a larger scale. And this time, we're gonna use, obviously, the large spool, and we're gonna use this 2x4 as our pencil windy thing.
Coil some bungee cord, feed it through.
Ready?
Yep.
Okay, here it comes.
There we go.
Got it?
Haha, yeah.
Add a washer and a long 2x4 to act as our pencil.
And now we stick the giant 2x4 inside the coil.
Just about. Yeah, we got it.
There
Okay,
we
cool.
go.
And we're ready to try it out.
So it looks like we're ready to go.
Yeah, exactly.
Do you want to do it in here or you want to do it outside?
Oh, definitely outside.
Okay, let's go.
Yeah, okay, cool.
Yep. Oh, it's heavy. Batteries are great at storing energy. They store electricity. Batteries? But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the pits, the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. Here's a fun chain reaction you can do with popsicle sticks, or craft sticks, because these ones are a little bit wider than popsicle sticks. It is because these kind of sticks are slightly bendy, and when you bend them and put them together in a pattern in a certain way, you can keep them under tension, and then they want to snap back, and then they'll fly. So here's how you make the pattern. Ready? You take a popsicle stick or a craft stick, and you put it down on the table. I know, okay, it's a slow start. And we take another one and put it across. Now comes the secret. The secret is over and then under. You want to put it over one and then under another, like that. And then this one, over, under. Put it over the one that looks like it's the top stick and under the stick that looks like it's the bottom stick. And then it starts to hold tension. It starts to hold the potential energy. Continue this pattern. Each stick goes over and under the two sticks at the end. Now here's the trick. Soon as this one lets go, then that one will let go, then that one, then that one, then that one, and that's how you get the chain reaction. They all start flying up. So you have to build it with never letting go of that last stick. You gotta always remember to keep a hand on it, or else you'll have to start again. So, okay, so you ready? You wanna see me let it go? Here we go. I know, that isn't so great because it's better if it's a longer chain. So fortunately, I have a longer chain. I've got a binder clip on this end, keeping the craft sticks together. Ready? 3, 2, 1. Wow! Release of kinetic energy from the potential energy of winding all the craft sticks together. Fun, and you can totally do it at home. Now, let's max it out. Behold, almost 800 craft sticks in a long, nicely designed triangle. Ready? 2, 1. Yeah! Craft stick chain reaction. I'm gonna go get something to clean this all up with. All right. So Anthony and I have built a giant spool racer and have taken it outside to try it out. In order to wind it up, we flipped over the last version on its side. But this spool weighs 200 kilograms. Easy to roll, almost impossible to flip over.
Come on, get it.
I don't think it's gonna work. It's too heavy to move.
Yeah.
We should have thought of that before.
Well, I'm sure we'll think of something.
So Anthony and I thought about it. And thought about it. And thought about it.
I got it!
What?
No.
But you... And the answer finally dawned. What if we roll it this way? Because then that would wind it up, right?
That's brilliant!
By rolling it backwards, we wind up the bungee cord in one direction, which will make it want to unwind in the other direction. Anthony and I roll it across the parking lot to get it wound up tight.
I don't think I can hold it anymore.
Okay. Let go. Okay, it's wedged.
It worked.
All right, one more thing. We're gonna hook the trike up to this one as well.
Okay.
So right now, it's all wound up, and when it gets moving, the potential energy in the coil will turn into kinetic.
Exactly.
Kinetic energy. Now, just in case you're tempted to try this at home, I need to tell you, do not try this at home. We're trained professionals, right?
Yes.
Yes. Well, as much as anybody can be trained for this, because no one really does this.
Are you ready?
Ready?
Okay, here we go.
Whoa. It's working!
It's working!
Yeah! Sure enough, all the potential energy we stored in the bungee cords starts to unwind, which rolls the spool and pulls me along behind it.
What's more, that big heavy spool has a lot of momentum. So when it gets going fast, it just wants to keep moving. It wasn't long before I had to jump off.
Amazing!
All right, that had a lot of kinetic energy.
That was a ton of kinetic energy.
There you go, Science Max, experiments at large, massive spool racer. Your turn next?
Yeah?
Okay. So that's what we're gonna do today, Science Maximites. Whoa! We are going to learn how to juggle. I can't hear you, I've got dominoes in my ears. And you put it in, and whoa, and now it's all broken. Well, here's the trick. Here's the trick. It's me disappearing. You see? When it would, blooper reel? Blooper reel.
Okay, hi.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Taking something flimsy and making something strong.
Whoa, pasta bridge!
We build things out of pasta, sand, and paper to show how you can use science to make something strong out of something weak.
Dry sand, wet sand, science sand.
It's all how you build it. Today on Science Max, experiments at large.
Oh, hi, Science Maximites. Have you ever been eating pasta and wondered, what could I build with this? Could I build something that could hold an impressive amount of weight? Well, I have. And that's what we're gonna do today on Science Max Experiments at Large. But we're not gonna use cooked pasta because it's too delicious. We're gonna use uncooked pasta, which is less delicious, but it's great for building. We're gonna make a pasta bridge. Here's how you do it. First, you wanna start with a plan. And then you want to take your pasta, I'm saying pasta, but of course spaghetti is usually the best thing to use, and lay it out on your plan. The reason you have a plan is so that you can make sure all of the spaghetti is exactly the right length. Lay it out on your plan, perfectly aligned like that. There. And now it's time to glue it all together. Now you can use white glue, but it takes a long time. So I suggest a hot glue gun, but make sure you get an adult's permission before you use one of these, okay? So you take your plan, you lay it out, you glue it up. Don't glue it on the paper because that will be bad. And you will end up with your truss, and it looks just like this. Now remember, you want 2 sides because those are the sides of your bridge. And as you can see, I've used several strands of pasta because that'll make it a little bit stronger. Once you have your trusses, it's time for the next part of the plan. This is the roadway, and it works the same way. Lay out your pasta, glue it up, and bam, there it is. Now, you put your trusses on your roadway, and you glue them all together, and you also want to put some struts along the top here, probably, to keep it nice and rigid. In the end, you will end up with a fantastic-looking pasta bridge. Pretty good, huh? Pasta bridge. No other bridge could claim to be 100% pasta. Minus the glue. 99.8% pasta. 0.2% glue.
I say there, Captain. Set sail. Set sail for the land of pasta bridges.
Now, if that was pretty fast for you, don't worry. All the instructions are gonna be on our website. Now, a bridge isn't a bridge unless it spans a gap, because that's what bridges are for. So you put your pasta bridge up there across the books like that, and then you can see just how much weight the bridge holds. It's pretty impressive. If you build it right, even something as flimsy and as delicate as pasta can hold quite a bit of weight. I like to use big, heavy blocks and put them in the middle where there is no support from the books whatsoever, and just keep adding heavy things and see how much weight the bridge will hold before it breaks. How much will it hold? Well, I'm not gonna tell you. That's where you get to be Science Maximites and find out for yourselves. And now, we're gonna max it out. Today on, oh, my pasta. Today on Science Max Experiments at Large, we're gonna be looking at how fragile things can become strong if you build them right. We're also gonna be maxing out the pasta bridge experiment to see if we can make one that's strong enough to hold me. You think we can do it? I know I have no idea, but I'm going to the Center for Skills Development and Training to find out. Oh, hey, Kyle.
Phil.
How you doing?
Great, thanks.
Awesome. This is Kyle. He's got a master's in civil engineering. Did you want some pasta?
I'm good.
I can go back and get some more.
Really, I'm good.
Okay. So what does a civil engineer do?
Well, a civil engineer builds the world around us. Talk about our homes, keeping us warm in the winter, our roads, hey, even our bridges.
Bridges, that's fantastic, because that's what I need your help with. I want to max out the pasta bridge.
Awesome.
I want to make one big enough that I can walk across it.
Okay, that's never been done before.
I know, right? You think we can do it?
We're gonna need a lot of help to do that.
We don't need help. All we need is a lot of pasta, which I have. Ha-ha!
Nice.
What do you say?
Yeah, let's give it a shot.
Okay, we'll give it a shot. Why don't we just take some to start, and then...
In order to max out our pasta bridge, the idea is to take many, many strands of pasta and just keep gluing them together so the long beams of pasta in our giant bridge is nothing but many, many regular-sized strands of pasta. Here's where we were after 20 minutes of gluing.
There, that's nice.
Yeah, I think this piece is done.
Okay, so how does it work? Is it strong? Whoa.
Well, let's give it a go, eh? Yeah, I think this will hold.
Great. So we just need to build a few more of these then, right?
Yeah, that's right.
How many more?
212 more.
212 of these.
More.
212, but it took us like 20 minutes to make this one.
Yeah.
Oh, well, I guess so. I mean, this is Science Max Experiments at Large. That's what we do. We just keep building, and, you know, I don't have any plans for the next while, so...
Phil.
Yep.
I think that there's a better way of doing this.
I would be delighted to know there's a better way. It'd be faster than this.
Much faster.
Sure, let's do it.
Awesome.
I'm just gonna put the pasta back in the bag because it'll
Phil,
get stale.
You don't have to do that.
No, but it'll get stale.
Phil, I'm gonna call in one of my friends. We're probably gonna need some more help with this.
Oh man, that's a great idea. Sorry, that's a great idea because
Yeah.
Because at least we could get your friend to help clean up.
Better sandcastles in 80 seconds.
Building sandcastles is fun, but you can't use dry sand because it doesn't stay up very well. You have to use wet sand. But even if you use wet sand, it doesn't hold a lot of weight. But if you use sand with the power of science, it does hold the weight. Dry sand, wet sand, science sand. Here's what's going on. Say these ping pong balls are grains of sand. When they're dry, they don't hold together very well. That's why you can't build a sandcastle out of dry sand. But if you get the sand wet a little bit, the grains of sand will hold together a little better because of the surface tension of the water. That's why it's easier to build a sandcastle with wet sand, but they still won't hold much weight. But if you add something that creates even more friction between the grains of sand, like say this sandpaper, it will hold the weight. So here's what you do. Take window screen and cut it into circles. Make sure you get an adult's permission first, okay? Deal? Put in a layer of sand, pack it down, and put in a circle of window screen. And a layer of sand, pack it down, circle of window screen. Then, you guessed it, layer of sand, pack it down, circle of window screen. The window screens are gonna add more friction between the grains of sand and will make your sandcastle strong. Strong with the power of science. And then, you can put lots of weight on it. And there you go. Sand with the power of science. Ha ha! Okay, I had to max it out. let's see how strong science sand really is. Huh? Science! Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan. Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer, though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't
All
forget
right?
to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this?
Yep. It helps the pasta to stick together. So as we're rolling, we're rolling, we're rolling. We're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thick
Yeah,
when we're finished with it.
exactly.
This is going to be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta, and the little bridge will be.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome. The shape of something makes a big difference in how strong it is. Get some toilet paper rolls and put them in a square, and then stack books on top of them. They can hold weight. Thing is, they can actually hold a lot more weight than you probably think. In fact, the amount of weight just paper in a tube can hold is really kind of impressive. Ha ha! And now, let's max it out. Phil's weight on 2 toilet paper rolls. Nope. Phil's weight on 4 toilet paper rolls. Nope. Phil's weight on 6 toilet paper rolls. Nope. Phil's weight on 10 toilet paper rolls. Oh. Ha! Ha ha! Phil's weight can be supported by 10 toilet paper rolls. But what if Phil jumps? Ha 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 ha. Didn't really work. Kyle and Michaela's plan is to use a long pole and sheets of uncooked pasta. We roll the pasta around the pole and spray it with a little varnish. We roll sheets and sheets of pasta along an 8-foot-long pole, making many layers of pasta. Then we wait for it to dry and remove the pole. What we have is an 8-foot-long hollow tube of pasta that becomes a single piece of the bridge. Then we attach a bunch of these pieces together and use more sheets of pasta to glue them into the shape we used for our small pasta bridge. we're making our giant pasta bridge by wrapping sheets of pasta around and around the poles using the technique we just had, making a whole large pole out of many, many, many sheets of pasta rolled around each other. And we've made a giant truss. Look at this. This is great, guys.
It's looking pretty good.
Yeah. If I hit it, you think it'd stay together?
No, stop.
What?
This is pasta, not steel. It's only made to just hold you.
Kyle, what do you think are the chances that this is gonna hold me when we build it?
Something like 50-50.
Not bad. Michaela, what do you think?
I'm gonna hope for the best.
Hoping for the best. That's exactly the kind of gray area we like to work in at Science Max Experiments at Large. Experiments at Large, I don't know if anybody's even ever done this before.
Not to my knowledge.
I don't think so.
Which is why we have no idea if it's going to work. Okay, so one more of these, because these are the sides.
Yep.
Roadway, and then the top.
Yep.
Yep.
All right, let's do it.
While we're waiting, it's a good moment to point out one of the things that makes our bridge really strong. That is triangles. As you can see, the truss, or the side of our bridge, is really just 3 big triangles. Triangles are very strong shapes to build with, and they work great in bridges.
Now it's time for Science So Simple, a caveman could do it. This is a caveman. Today we're going to teach this caveman how to build a strong structure. Here are some boxes. Go on and build a shelter, and I'll come back and see how it worked out. No, that's not right. You need to build walls by stacking boxes on top of each other. That's how you build. Understand?
Oh, yeah.
I'll come back later and see how it worked out.
Yeah.
Uh-oh. Does that look right to you?
Yeah.
Look at those boxes. They're stacked on top of each other. But if they are in tall stacks, what would happen if you push on the wall? You see? Walls don't stay up if you build like that. Let's try again. I'll help you this time. First, lay out the foundation, where your wall should go. Good. Now let's make the second level. No, don't put it right on top. You need to stack in between. That's how you make a strong wall. Okay, I'll come back later. Nice work. Why don't you give it a try? Looks strong, but you forgot a box. Join us next time when we talk about how to make a door.
Building a door in a wall is hard, because how do you make a big gaping hole in your wall without your wall falling over? Well, people have come up with lots of ways to put doors and windows in walls made of stone blocks over the centuries. And you can do this at home with books like I'm doing, or with building blocks. Just go up until you're happy with the height, and then stack each next layer a little closer to the middle until the final layer touches just like this. And then you take a big heavy book and you drop it right on top. And it's pretty stable, and you've just made a doorway. It works even better if it's part of a wall, because you want extra weight on the outside of these books here. So of course, I had to build one that was part of a whole wall. This is the same corbelled arch built out of little building blocks. And as you can see, I went closer and closer together until it meets at the top, and it is very strong. Whoa. Ha-ha! Now, let's max it out.
The kind of arch we're building is a corbelled arch. And the Science Max build team and I are using pieces of wood cut to different lengths.
How high can it go? We can use my head to, no, okay, wait.
It takes a while to get together, but once it's done, it looks just like the kinds of doorways stone buildings had in ancient times.
Ta-da! There you go, a maxed out corbelled arch. We went straight up
until we got to these layers, and they got a little bit closer and closer to the middle until the last piece is one big solid piece. And if we built this right, it should be strong enough to hold me up. Yeah! Science! Woo-hoo! Well, it held me up for a minute, didn't it?
We rolled our pasta and constructed one truss. Now we've made a lot more rolls of pasta and connected them all together to make a second truss and a roadway, as well as the cross braces on top. And when we get it all together, we end up with...
Whoa! Pasta bridge!
Pasta bridge!
We did it! We built it. We have no idea how long it will stay up. But it's up. It's doing its bridge thing for now, anyway.
I am very excited because, as far as we know, I'm the only one to try to cross a bridge made out of pasta. What do you guys think?
I think I don't want you to be the last person to cross a pasta bridge.
You're absolutely right, but I'm gonna do it. I think we're ready. Yeah?
Yeah.
Okay. Here we go.
Ah!
Oh no, that doesn't bode well for our pasta bridge. What happened here, Kyle?
You put all your weight in the middle of the joist. It snapped.
If only there was a way to distribute your weight. Maybe if you crawled?
Do like the military style kind of.
Oh, right, so that I'm putting my weight on more than one spot.
Yeah,
Exactly.
Oh, wait a minute. That gives me an idea. You guys stay right there. I know what to
Okay.
do. I know what to do. I know what to do.
You're coming back, right?
Skis distribute your weight over a large area so you don't sink in the snow. That's what skis do, which is perfect for the pasta bridge.
Come on.
Okay, here
Come
we go.
on.
Carefully.
Is it working?
It's working.
I hear some cracking.
This might do it.
Try to spread your legs apart.
Spreading my
Distribute
legs
your weight.
apart.
Distribute your weight.
Distributing my weight. It's swaying a lot.
Oh, man.
Whoa.
Crossing the pasta bridge!
Woo, high fives. There you go. Science Max, experiments at large, pasta bridge, skis. What more could you want? Maybe a pasta chairlift of some sort. Science! Wear it. It is the fashion accessory of the year. I want to travel down it. Should have made it bigger. Science! 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 How long do I hold this piece for?
A long time.
Guys? Guys? This isn't fun anymore, guys.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, experiments at large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster, and then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the Dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxadrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the Regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built, and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind this small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing
reaction.
this bit now. We're doing that bit in a minute, so we could. No, I said we're doing it later. We're doing it later. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock car?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is I would, in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
You did.
You did let it go.
I let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's a
they
good
can hold the
idea.
tank, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity. He gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites, you can get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool and I realized I should have duct taped the pocket because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's third... No, hold on. Newton's third law. Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're gonna be using next for our air-powered car. Got it?
Yep.
All right,
Good.
so Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. Okay. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls, and I think it's gonna work the same way. Let's find out. You throw one out, and ha-ha! Yeah, it works the same. Okay, now let's try it with two balls. Okay, we ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube, and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Wait, I can play Mary Had a Little Lamb. It's working! It's working! Newton's cradle out of bowling balls. Come on! You know this one, sing along. Whee! Come on! I mean, come on!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about elastic energy. We use it to build a catapult and a paddle wheel boat, and then we max them out. We even learned some history. Elastic energy. Today on Science Max, Experiments at Large.
Welcome to Science Max Experiments at Large. I'm Phil McCordick, and today we're going to be building one of the most devastating, one of the most powerful machines known to medieval man, using a plastic spoon, among other things. We're going to be building a catapult. Catapults were used throughout history for all kinds of reasons, to throw all kinds of things, but mostly big stone blocks at castle walls in order to knock them down. Here's what you need in order to build your own catapult. You need elastics, pencils, unsharpened is fine, plastic spoons, like I said, and popsicle sticks. Popsicle sticks. Popsicle sticks. I'm gonna go wash my hand. So, here's the science behind what we're doing today. It's all about elastic force. Elasticity is a property of solid materials, like this elastic, and how much they tend to return to their original shape when deformed, like when I pull on it. Elastics are called elastics because they're great at doing just that. You can pull on it and pull on it and pull on it, and it'll, always return to its original shape. So we are using the power of elastic force today. Ow.
Now it's time for a Science Max quiz. Elasticity is the ability for a material to return to its original shape when deformed, like this or this. Which of these materials have elasticity? A rubber band, a pencil, or a rock? Haha! This is a trick question. The answer is all three. Most solid materials have elasticity. Nearly everything will deform a little and still be able to return to its original shape. It all depends on how much. This is a steel bar. This is an elastic band. And this is an ice cream sundae. We're not talking about ice cream sundaes now, though. So get that out of here. Good. Now, a steel bar and an elastic band both have elasticity. A steel bar can be stretched to 1% of its length and still spring back. A rubber band can be stretched 300% or more. The difference between the two is why we make balls out of rubber and buildings out of steel, because the other way around wouldn't be good for balls or buildings. This has been a Science Max quiz.
All right, let's build our catapult. The first step, take 4 pencils and stick your popsicle stick in between so you have 2 on the top and 2 on the bottom. And then use your elastic to go around and around and around. That's why I like building things with elastics, because it makes it very fast to tie things together, because once you go around and you have it nice and tight, you just pop it over the end and voila, it stays together. And that is how you start making your frame. Put more pencils on that side.
And another popsicle stick on the other end, held on at the corners with more elastics. Then, take even more elastics and put them right around the middle until you get
this. I've added a few more elastics around the middle here, and that is where we're gonna get all of our elastic force. I think I have 6. The more you use, the better it's going to work. Take your popsicle stick, stick in between the elastics, and then start spinning it around. Here's the reason I use pencils and popsicle sticks, is because the pencils are a little bit longer, which allows you to twist the popsicle stick around in the middle and build up the elastic force. Now, because I'm twisting, the elastic force we're using here is called torsion, or twisting force. When you feel you have enough torsion, pull your popsicle stick down a little bit so it won't unwind on you, and you'll see that you have all kinds of elastic energy. Then take your spoon and stick it on the popsicle stick, and you can also break off the popsicle stick if you want to make sure it's the right length. And it works like that. To make the frame, you just need more pencils and elastics. The trick is to make a triangle with 2 pencils attached to your frame. They should stick up right where your catapult arm would be fully upright. Then, take a final pencil and put it across the top. Don't forget to pull the arm back before you put the pencil across, otherwise it'll end up on the wrong side. Now, this is very complicated and I went pretty fast, so if you want the step-by-step instructions on exactly how to build this, go to our website. And there you go, a catapult of your very own that you can use to knock down very small castle walls. I've also built a larger catapult using all of the same principles. Pretty good, huh? It's got a longer arm, which means I can throw marshmallows even further. Whoa. Or I can throw larger marshmallows, or I can throw very large marshmallows. Now I know what you're thinking. You're thinking, Phil, is that the largest catapult you're gonna make? Well, of course not. This is Science Max, experiments at large. I'm headed to the Center for Skills Development and Training, and we're gonna max out the catapult so that it's big enough to throw one of these. Hey, Zach.
Hey, Phil.
How you doing?
All right.
This is Zach. He's a mechanical engineer, and you build machines for a living, right?
That's right.
Great, because I need help building a catapult.
Okay, but what's with the pumpkin?
Well, the pumpkin is what I want to throw out of the catapult. See, I figure we just take the small design and we just make it so that we can throw one of these. What do you think?
You're gonna need a really big catapult.
Yeah, and I'm also gonna need some really big elastics. Where do you get those?
Well, in medieval times, they used rope to make large catapults.
Oh, okay, well, rope is a lot easier to get, and that would be fine. And I want to make this arm as long as this piece of wood here.
This is gonna be a huge catapult.
It's a huge catapult. I guess we should build it outside, though, huh?
Let's do it.
Okay, it's over that way.
Okay.
I'll follow you.
Sure, do you want a hand with that?
No, I'm fine. You go ahead, and
Okay.
I'll just, maybe if you hold the door open for me, I could just hold, no, you know what, you go and I'll meet you.
You sure you're good?
Our full-size catapult is going to look a lot like the popsicle stick version. We start with a 4-sided frame and add some legs on the bottom. Our spoon is going to be replaced by a long throwing arm with a basket on the end. Then we need a really strong cross brace at the top to stop the arm. Just like in the small version, using a triangle shape is the best because triangles are very strong. Finally, we need something to wind around and around, which is going to give us our elastic force. Instead of elastics, we're going to be using rope for our catapult because rope has just the right amount of elasticity. But unlike medieval times, we're going to be catapulting pumpkins. Once Zach and I got it all put together, it looked like this. Okay, we have built a catapult. Check it out. It's pretty solid, and I think it's pretty amazing. And just like in the small catapult, we have our elastic force. But this time we're using rope, right, Zach?
Yes.
Okay, and rope will work as well as the elastic did in the small one?
Yeah.
All right, great. So what do we do? It's really loose now.
We need to wind this up so that we put some tension into it.
Go!
The reason a catapult works is because the rope is twisted. The elasticity in the rope wants to unwind, which gives the catapult its power. Just like the small catapult, the more you wind it, the better it works.
Good. Usually in medieval days, they had whole teams of people doing this job, but it's just me and Zach now. How you doing, Zach?
All right.
Okay. And then we clamp it on here. So the thing doesn't unwind, right?
Yeah.
Good. All right, now we have our pumpkin, and we're gonna fire our pumpkin in our castle wall, which is made out of cardboard boxes over there. Pumpkin. All right, here we go. Pulling the arm back. Oh, that elastic force is pretty strong. Okay. How do you think you think that pumpkin's a good size?
Oh, it's pretty big.
You think?
Oh, a little too big.
It's too big for our basket.
Yep.
Smaller pumpkin! Smaller pumpkin! I'll hold this. No rush, Zach. No rush. Okay, rush, Zach. Can't hold.
Oh, yeah.
Can't hold arm. Okay, ready? 1, 2, 3! It didn't work that well.
No, not quite that well.
Yeah, so
Let's see.
it went and it flew and it landed here, which is a little farther away from the wall than I'd like it to be. 1/3 of the way to the wall! I don't know if that's enough. What do we do to make it better?
Well, the way we're throwing it right now, we just have the pumpkin in a, at the end of the arm. But if we make some kind of a sling so that we fling it as we're bringing it up.
We make a sling?
Yes.
All right, I don't know how to make a sling, but you know how?
Sure.
All right, we'll make it and then you can explain how it works.
Yeah.
All right, good. Let's put the pumpkin over here. We'll recycle it later.
Max Historica.
Good morrow to you. I am Lord Fillington III, and welcome to my medieval castle. Throughout history, lords and kings have built castles and walls to keep people out. I built my castle to protect my prize collection of snow globes. I have so very many, and they're all mine. Ha ha! Oh, hello! You down there! You can't come in. This is my castle.
And throughout history, there have been people who've been wanting to get into those castles because Lord Fillington has been hogging all the snow globes, and I'd like to look at them. But the hard part is figuring out how to get into the castle, because I can't just come up to the wall and start hammering on it. Huh?
Taste the wrath of my water balloon!
Because if I get too close to the castle, he can get me. Ha 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 ha! Fortunately, there's this thing called a catapult.
Oh, fiddlesticks. They have a catapult.
What you do is you put something heavy in the end here, and the catapult fires it at the walls of the castle, knocks them down, all from far enough away that the people in the castle can't get to you. Ah! Oh, I surrender! Don't knock my walls down! It'll take me all week to fix them. Oh. All right, you can have a snow globe. Oh. And that's how catapults were used in history. Oh, so beautiful. Back to our maxed out catapult. Our first design threw a pumpkin just like it was supposed to, except it only threw it 1/3 of the way to the wall. Now Zach and I are planning to outfit the catapult with a sling. The sling attaches to the end of the throwing arm and gives the pumpkin a lot more distance to travel. Because the pumpkin is traveling a longer distance in the same amount of time, it will be going faster, which will hopefully get it to the wall, or at least a lot farther than before. So we built this sling. How does this work, Zach?
Well, we've got one end tied here.
Yeah.
And then we put the pumpkin in here.
Wait. Okay, pulling arm down. Pulling arm down. Okay, yeah, now what?
Now we put the pumpkin in here.
Put the pumpkin in there.
Yeah. And then we loop this over the back of the... Over that. As the throwing arm goes up, this will slide off the back of the throwing arm and it will release the pumpkin.
All right, you're the expert. I believe you. Let's try it out. 3, 2, 1. Whoa! Okay. That works really well. You know what the problem is, though? We still don't have enough oomph.
Yeah, it needs more power.
So what do we do? I don't know if we can crank that rope anymore.
I think we're at the limit of our rope power, but if we added some more elastic...
I thought we weren't going to use elastic.
Well, we used elastics in our small demo model, so what if we use some more?
We have elastics? I don't know
yeah,
if we
brought
have...
some in here just in case.
What's this?
It's surgical tubing.
It's like a giant elastic. Mm-hmm. Well, I guess this is elastic force. So do we twist it around at the bottom there?
Well, we just wrap it around the throwing arm like this.
Oh, I see. So we tie it here.
Yeah, we just need a lot more, and then
we pull this, and it would be. Oh, yeah, that would make a lot more. So we just need a lot more of this elastic. What is this again?
Surgical tubing.
Surgical tubing. It's like a giant elastic. Fantastic. All right.
Goggles on.
Goggles on. Yes. Here's another fun way you can play with elastic force. Take a milk carton. I prefer Science Max milk because it's the creamiest. 2% cream, 100% science. Wrap some elastic bands around it with some popsicle sticks on the bottom, sort of like feet. Then take some clamshell packaging, which wraps just about anything you buy nowadays, and cut out a square or a rectangle. Then wrap some tape around that square with an elastic in it and put the elastic on the feet of your milk carton. Then wind it around and make sure you go backwards so your paddle wheel boat will go forwards when you put it in the water. And there you go, a paddle wheel boat. Now it is time to max it out. Ahoy, the SS maxed out elastic force paddle wheel boat mattress. I need a better name. But I've made a giant paddle wheel boat that will work on elastic force because I've got surgical tubing as my elastics, and that's an air mattress. And then I use some lumber to hold it all together. And of course I need a paddle wheel, and what better thing to use in a pool than a flutterboard? Okay, here we go. So normally you're not allowed to wear your clothes and your shoes in the pool, but I got special permission because of science. Besides, I'm not worried at all, so I didn't wear my swimming outfit because I figure I can totally do this entire experiment without even getting wet. That is how confident I am. All right, now the tricky part, we'll be getting onto the mattress. Okay, here we go. Ha-ha! Whoa. Ha-ha! The SS Science! Hey, SS Science, that's a great name for this. Look, it works great, and I managed to stay totally dry. Huh? Well, almost. Whoa, oh, oh. Haha, you thought I was gonna fall in the pool, but I didn't. Uh-oh. My flutterboard has stopped moving, and I'm in the middle of the pool. Almost. Yeah. Didn't think this through. No. 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 No, that's not going to work. Maybe I'll wait. Our maxed out catapult was working well with the sling we attached to it, but it still didn't make it all the way to the wall. Zach's idea is to attach a bunch of surgical tubing to the cross piece of the catapult. Surgical tubing is pretty much big elastics, so we'll have two places we're getting elastic force from, the rope and the surgical tubing. Hopefully this design is enough to help our catapult fling a pumpkin far enough to hit the castle wall. All right, here we go. You hold that. I get this. We got our system down now. Okay. This goes up to there. Okay. Okay. 3, 2, 1. Nope. One, 2, 3. Oh! Oh! It went too far. It went too far. That's so good. Oh man. Right. Okay, so all we gotta do is move the catapult back. So you get that side, I'll get this side, and we'll move the catapult. See, now our catapult is too good. We gotta back it away from the castle. All right, let's go again. Aha, pumpkin.
Pumpkin.
Pulling arm back.
Pulling arm back. Grunting.
Loading. Pumpkin. Hooking rope on arm.
Hooking rope on arm. More grunting.
More grunting. Pulling back strongly. 1, 2, 3. Oh. Oh. Oh, wow. Woo.
We're inside the castle.
We're still inside the castle. Oh man, it's an excellent shot though. So what do we do? Move the catapult back?
Yeah.
Move the catapult back! Right about
here?
Here. Here we go again. Pumpkin!
Pumpkin.
Loading arm.
Loading arm.
All right, you ready? You think it's gonna work? We've done every modification we can possibly do. So you think it's gonna work this time?
We did it, it's gonna work.
Okay, here we go, I'm excited. All right, ready?
Ready.
1, 2, 3. Whoa! Yeah! Woohoo! High fives! Well, there you have it. Awesome job. Now we need to throw fingers to see who gets to rebuild the castle. Okay? 1, 2, 3. Oh, thanks very much for joining us. Let's take a break. I'll rebuild the castle. You see, this is exactly how catapults used to work. They'd hit the same part of the wall over and over until they made a big hole, and that would weaken the wall. Fortunately for me, it's really easy to fix. Just put this right in here. Oh, man. The pool will be closing in 5 minutes.
No, I'll do it. No, why do you ask me?
Taste the wrath of my water balloon! I don't believe it really sells it if he doesn't smash the water balloon. Does he? Good moral to you! I got my feather in my face. Oh, you gotta be kidding me!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
Today on Science Max, we're looking at
Chemicals!
Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Whoa! Woo! Cutest science ever.
Today on Science Max, experiments at large.
Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be Science Maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today. Chemistry in all its forms. And of course, because it is Science Max, experiments at large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You can grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome. Chemistry. Okay, so I want to use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I want to mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. We gotta. No, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. Just one more. Okay, good. Okay, good. Yeah. I took too much. Uh-oh. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. Chemicals? Chemicals. Chemicals? Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, chemicals. 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 Me, chemicals. You, chemicals. Ramona, chemicals. No, I said your chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talini, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our third bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh, yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar has 5% of this and 95% water. But this is 100%, so it's much stronger.
Much stronger. Can you put this on your French fries?
No, I wouldn't be putting it on your French fries.
No? As chemicals go, how dangerous is this?
It's not too dangerous, but you definitely don't want to be breathing it in, and you don't want to be eating it.
Or getting it on your skin. That's why I'm wearing these fancy gloves. So what I'm gonna do is I'm gonna pour the acetic acid in this. What's this called?
That is a graduated cylinder.
Because it finished school. So it graduated. Now you're gonna mix water and food coloring and soap all together.
Yep.
And pour it into there?
It'll help dissolve some of the baking soda, so hopefully it'll react better with the acid.
Sounds good. Face protection.
Oh.
All right, that's good. And now, when we do it, I want to add the funnel at the end to like accentuate the concentration of, but I don't know if it's gonna go so fast that I won't be able to get it in there, but we'll try it.
Try it.
Vinegar, baking soda, volcano, version 2.
Good thing you got the mask.
It smells a lot like vinegar. It's really strong. Oh. That was pretty good. But what can we do to make it even bigger?
Well, you could try using a different chemical reaction.
Ooh, okay. Like what?
The decomposition of hydrogen peroxide produces oxygen gas, and so that one's pretty vigorous if you use a catalyst.
So we want something that makes a lot of gas so that it makes a lot of bubbles when you put the soap in it.
Yep.
Great, let's do it. And the sooner we leave that smell, the better, I think, for my taste. Today we're combining 2 different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. very cool, and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land?
No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry.
We've gone from vinegar and baking soda to 100% acetic acid in baking soda, and now we're doing the
Vinegar and baking soda volcano version 3. No longer vinegar and baking soda.
Nope.
What are we using this time?
So here we have some hydrogen peroxide.
Oh, that's the stuff you use at home to put on a cut, right?
Yeah, but the stuff at home is only 3%. This one's 30.
So much stronger,
Much.
10 times stronger.
Yes.
And is this more dangerous?
It's definitely corrosive, so wear your gloves.
Corrosive means it could eat your skin.
It can burn your skin a little
Which is
bit.
why we're wearing gloves and blast shields. What's gonna mix with this?
So here we have some potassium iodide, which is a salt, and it's mixed in with some water.
The most important part of this reaction is the fact that it creates gas.
Oxygen
which
gas?
makes bubbles when you put in dish soap, right?
Yep.
So one big squirt of dish soap like that. Mix it up. Now we go over to the blast zone.
That's plenty.
All right. Now that's a reaction. Looks like there's steam coming off here. Why is that happening?
Well, it is an exothermic reaction, so heat is being generated as the reaction proceeds.
Oh, cool. Can we lift our visors now?
Yep.
Awesome. And what's being released? What's the gas that's coming off here?
So it's oxygen gas that's being produced.
Oxygen. What we want to do is make this even bigger, but first, can we do it again?
Sure.
Because I have an idea. Hold on. I think we should repurpose our old volcano. What do you think?
Sounds like a good idea.
Okay, so if we put it over here. All right, volcano version 3.5. Hydrogen peroxide, potassium iodide. Right, here we go. Whoa!
Looks like lava.
Whoa! Look at that. Now that is a big volcano eruption.
Just covered the town.
That is completely, yes. That town is gonna be very clean because it's all soap bubbles. It's the cleanest volcano this side of Science Maxville. So I still think we can do this bigger, though, right?
I agree.
Oh, I know. What if we use some sort of a tube, like maybe one of these, right? And then we attach it to like an air compressor.
I think you'd get some height.
Yeah, and we go outside.
The atom in 60 seconds.
The atom is the smallest unit in a chemical element. Atoms are made of 3 parts. Part number 1 are these guys, protons. They have a positive charge. The number of protons determines the element. 1 is hydrogen, 2 is helium, 3 is lithium, and so on. The protons sit in the middle here, which is called the nucleus. They sit in here with part number 2, these guys. They're neutrons and they have a neutral charge. Now I've got 8 protons and 8 neutrons in this nucleus, making this an atom of oxygen. Orbiting around the nucleus are these tiny guys. They're electrons and they have a negative charge. I will demonstrate using kittens.
Kittens are perfect because just like electrons, kittens are really small. And just like electrons, kittens move around randomly. You never know where they're going to be, but an oxygen atom should have 8 kittens, or electrons, somewhere inside. These kittens are constantly escaping, but guess what? That happens with electrons too.
There you go, the atom, a nucleus of protons and neutrons surrounded by randomly moving electrons. Cutest science ever. How do you guys feel? Did you learn something? Huh? Pause up. Who learned something? Hmm?
Talina and I have made a bunch of chemical reactions, but in our quest to max things out, we've got a new plan. Hydrogen peroxide and potassium iodide create gas. One way to max out the reaction is to contain the gas in something like a tube. We're gonna put the hydrogen peroxide in the tube first. Then we're gonna put in the potassium iodide in the top through a one-way valve. Then we're gonna pressurize the container. When it finally reacts, it will shoot up through the valve and we'll see how high we can get our stream of bubbles to go. But be warned, capping anything and not letting it escape is never a good idea. So we've got a release valve to make sure things work out. This is one of those experiments that's definitely on the list of don't try this at home.
Vinegar baking soda volcano version 4. Hydrogen peroxide, potassium iodide. And what we're gonna do this time is we're gonna put it in this tube. Hydrogen peroxide goes in here. And we've got, Talina, do you have the potassium iodide in syringes?
Yep, 2 syringes full.
2 syringes full. About there is good. And then soap. Good amount of soap in there. And so what we're gonna do is we're gonna close this off and tighten it up. And then we're gonna pressurize the whole system. And then we're gonna add the potassium iodide. And it's going to be spectacular, we hope. Okay, that's on tight. This is all good. Putting this down here. And potassium iodide goes in here.
Ready?
Puts down. Ready? 1, 2, 3, go. And we back away slowly. Whoa! Whoa!
Yeah, that's what I'm talking about. Okay, let's check it out.
Woo! All right, there you go. Vinegar and baking soda volcano maxed out. Thank you, Talina. That was great. If you guys want any instructions for the stuff that we've done today, they're all on the website. And thank you very much for watching Science Max Experiments at Large. We kind of need to clean up a lot, don't we?
Yeah.
We have out here, we have the other room. So tell you what, you get a mop, I will get the hose and a wheelbarrow for the suds.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Chemicals! Chemicals! The chemistry of hydrophobic coating literally repels water molecules and doesn't let her... Chemicals! Chemicals! Hydrophobic coating... Bleh. Chemicals! Yeah. Chemicals.
2 carbon, 2 oxygen, 4 hydrogen?
Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about hot and cold. A giant hot air balloon, dry ice, the coldest temperature possible,
Absolute 0.
and whatever this is.
Blubber suit!
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. We're gonna be making one of the easiest and one of the hardest experiments to do. Here's what we're gonna make: a hot air balloon. And it's pretty easy to make. That's why it's one of the easiest experiments. All you need is a plastic bag, but not any plastic bag. The kind of plastic bags you get at the grocery store to put your fruit in. That kind of plastic is very thin, very light, good for hot air balloons. And you just want to put 2 paper clips on the bottom of the bag to hold the bottom down. Now here's the other thing you need. You need an adult and a hairdryer. Turn the hairdryer on, put the heat on the highest setting and the fan on the lowest setting. The air inside the bag is getting hotter, which means the molecules are moving faster and they're getting further apart, which means there's going to be less of them in the same space. Less molecules means less weight, and that means it's going to be lighter. The bigger the difference in temperature between the air inside the bag and the air outside the bag, the better it's going to work. So I recommend doing this outside, actually, on a cold day. When it's been long enough, turn the hairdryer off and it will float. Haha. Now it won't float very long because the air inside the bag will quickly return to its original temperature and it will no longer be any lighter than the air outside the bag. But it's definitely fun to fly for a while it lasts. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna max out the hot air balloon and make a giant hot air balloon. Yeah, I know what you're thinking. You're thinking, Phil, they already exist. Why don't you just get a giant hot air balloon? I mean, they're big and you... No. There's no fun in that. I want to make one I built myself. I don't think I'm going to be able to fly in it, but it'll still be pretty cool, I bet. I just need someone to help me. Oh, I know. Michaela from the Ontario Science Center. Hopefully she's not busy. Hey, Michaela, how are you?
Good, how are you?
Good. I was wondering if I could get your help with an experiment. Do you have some time?
Yeah, I'd love to help out.
Awesome.
Sure.
Okay, let's go back to Science Max headquarters and I'll show you what we're gonna do. Okay,
Nice.
So ready? Here we go.
Oh, no, still here. Still here.
Why are we still here? That's weird. Okay, I know. No? Why is the code not working?
I think it's the Science Center code. Try the
Oh, it's the lab code. Right.
Phil, are you okay?
Yeah.
Are you okay?
Yeah, no, I'm fine. So, Michaela, I'm glad you're here because today I want to max this out. This is my hot air balloon. It was better before. I smushed it in my pocket, but what I did is I used a hairdryer and then I put it in and I heated the air and then it rises up. So in order to max it out, pretty simple. I just get larger bags, right? And then I thought we could cut them and tape them together to make a much larger balloon.
It's a good idea, but you know, if we're making a hot air balloon, we need to make sure our materials are really light. The duct tape seems a little heavy. Even this bag seems a little heavy to me.
In terms of, oh, you mean
terms of
the
weight.
kind of plastic it is might be a little bit.
It seems really thick, this one.
Well, do you know for sure?
I've never tried it before.
All right, well, that's science. We should try it and see what happens.
Let's try it.
Okay, so I'll cut along the side of the bag. You see that? Carbon dioxide gas. Our bodies breathe in oxygen and breathe out carbon dioxide. Did you see it? Oh, take another look. How about now? No, you didn't see it, right? Because carbon dioxide is invisible unless you freeze it. This is dry ice, frozen carbon dioxide. And this is wet ice. It's not really called wet ice. It's frozen water. Now, you know what temperature water freezes at? Starts with a 0, ends with a, well, it's actually 0 degrees Celsius. And this freezes at -79 degrees Celsius. It's much colder. I have to hold onto it with a glove because if I held onto it with my bare hands, I get frostbite. So here's the experiment. If I pour some liquid water on the dry ice, will it freeze again? Let's find out. Because the dry ice is so much colder than the freezing point of the water begins to freeze. From the bottom up,
in room temperature air right before our eyes.
Whoa! Totally frozen! Cool! Cool.
In order to build our hot air balloon, Michaela and I are taking clear garbage bags, cutting them along the seams so they end up as one thin sheet of plastic, and taping them all together with duct tape into a balloon.
Okay, so that's how
Nice.
many bags is that?
It's like 12 bags.
Well, so you think that's big enough?
I think so. It's pretty big.
Okay, I think we can stop there. Okay, so where's the opening again?
I
I
think
hope
it's
you
on
didn't-
your side.
I hope you didn't duct tape it close. Okay, no, we're good. We're good. So it's going to inflate like this. Wait a minute. Let's make sure it works. Is it working?
Kind of.
I don't know if it's inflating. Okay, good. So it does inflate. It does hold air,
Yeah.
right? So should we try it?
Yeah, let's try it.
Okay, so we're gonna use a hairdryer, right? And now we wait. It's working.
Kind
right?
of.
Oh yeah.
Woohoo.
Okay, it's almost inflated.
All right.
Okay, what do you think?
Yeah, let's try it.
Okay, on the count of 3, we'll throw it, okay?
Okay.
All right. 1, 2, 3. It didn't quite,
Not quite.
doesn't-
Aw.
doesn't quite float,
It's
huh?
still too heavy, Phil. I think we got a couple problems here. The duct tape is really heavy.
Yep.
Also, these bags themselves are really heavy.
Okay, well, if we want to fix the duct tape problem, we could use lighter tape. Like, what if, we use invisible tape, or as I like to call it, science tape.
Science tape.
Which would be lighter than duct tape.
That's a good plan.
But what do we do about the bags?
Have you ever seen those, those dry cleaning bags?
Oh, wait, I've got one. I've got one here.
Cool. Perfect.
Aha!
Yeah, perfect.
Because, when I get my lab coats dry cleaned, so let me see here. Oh yeah, this is much lighter. This is kind of the same material as the grocery store fruit bags, right?
I have a better feeling about this one.
So lighter tape, lighter bag means a much lighter balloon. Okay, well, let's try it. First, I should probably take my lab coat out. This is water. Now, it's ice water. Science! Okay, no, that's not the science part. Here's something you can do at home. Get some ice water and a way to time yourself and stick your hand in the ice water. It's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects the seal and a whale. We don't have blubber, but we are today gonna have some blubber, because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this. And you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here I have 2 bags of blubber, and I've taped all the way around the outside. So I have, a blubber glove. Check it out. So, let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! I can't. Okay. Oh, here we go. In. Okay, so far. Oh. The legs are warm. And. Oh! Blubber suit! Ha ha ha! I am in seals! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah! Blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber, just like I do. Okay, so now, all I have to do is get out. Blubber suit! Oh no! My blubber is leaking! Ah, I've sprung a leak! My blubber! Oh, my precious blubber! No, what a world! Oh, hey, how you doing? Shut the door, it's cold out there. Cold enough for you, huh? Well, that's nothing. Let me tell you. You know what temperature water freezes at? Yeah, 0 degrees Celsius. But even that is nothing. Let's say it's winter in Winnipeg. It could get down to -20, maybe even -40. But even that's nothing. Liquid nitrogen, -196 degrees Celsius. But even that's nothing. The vacuum of space, -271 degrees Celsius. But even that's nothing. So, what's the coldest temperature? What's the coldest temperature you can have? It's called absolute zero, -273.15 degrees Celsius. At that temperature, all the little wiggling that particles do comes to a stop. Everything is frozen. No more movement, no more energy. Everything stops. It doesn't get any colder than that. Absolute zero is the ultimate nothing. Brr, time to get your mittens on. Our first hot air balloon didn't float very well.
It's still too heavy, Phil. I think we got a couple problems here.
So we're making a lighter version out of dry cleaning bags and science tape, both lighter materials than our last version. We also went for more of a square shape than our last version, which kind of looked like a sock. Once we were done assembling, we got the hairdryer and tried it again. Ooh, it's sort of working.
Kinda.
It's inflating. That's something.
It's a start.
It feels warm, like the hairdryer is actually making a lot of warm air in there.
Yeah.
This is definitely working better than the last version because it's so much lighter.
Yeah.
Wait a minute. Almost got it.
Oh.
Yeah, it's sort of working, right?
Cool. Kind of.
Okay. Ready?
Are we testing it?
Turning off the hairdryer.
Oh.
It It kind of collapses the moment we turn off the hairdryer.
Not what we expected, was it?
Yeah.
No.
I mean, it sort of works.
The thing is, our balloon is so big that we need to heat up all of the air that's in there. I don't know if this hairdryer is strong enough.
I think you might be right. So we just need something else that pushes heat.
Yeah, more heat.
So
More
like
power.
a heater of some sort. You know, we've got some heaters up in this room actually, and maybe I could just tear one out. We can use that.
I like it.
Okay.
Let's do it. All right.
There.
Got it.
An industrial heater. And this is going to work just the same as our hairdryer. It's going to blow a lot of hot air up here, but this is way more effective than a hairdryer, right?
Yeah, way more powerful.
So we put the balloon over here, hot air comes up, the balloon inflates, and hopefully flies.
Hopefully.
All right, let's get the balloon. So we put the balloon on the heater and turned it on. But it doesn't seem like much is happening. That's because the heater pushes less air, but the air is much hotter, which means it took longer. Should we have brought a book? But soon it was inflating.
Definitely a better result than the hairdryer.
Okay, you ready? I think it's gonna work.
It's gonna be awesome.
All right.
Yep.
1, 2, 3, let go.
Lift off.
Yeah! It's like a giant jellyfish!
That's huge.
Uh-oh, it's tilting, it's tilting. No! No! Oh no, it's going back down. Okay, so the balloon flies, which is great.
Awesome.
The problem is it turns over in the air.
Yeah, I noticed that.
And if it turns upside down, then all the hot air comes out and it doesn't fly anymore.
I was thinking next time if we make it bigger, what if we had a little weight at the bottom just to keep it stable?
Oh yeah, okay, I've seen balloons that have sort of an X, like a very light wood that goes across the opening at the bottom.
Oh, cool.
Maybe we could tie a piece of rope to that to keep it weighted. And if the bottom is heavier, then it won't flip over upside down, right?
Love that idea.
So we're gonna weight it at the bottom with a little X so that it doesn't flip over. And we're gonna make a bigger balloon.
We're gonna need more bags.
Oh, right, back to the bag store.
Bag store!
Okay.
Wait for me!
Being a chef is my absolute passion, and cooking up science recipes is my specialty. I'm Buster Beaker, and this is Cooking with Science.
Strange. This spoon is no sharper than it was before. Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker, and today we're cooking with coal. Today we're going to learn how to make a drink cool. Look at this bottle of lemonade. It's warm right now and not very refreshing. So what's the best way to cool this down? We put it in ice, right? But did you know there's an even better recipe than ice? You can make ice colder. It's true. All you need to do is add salt. I've got a second bowl of ice and a second jug of lemonade, and I've got 2 digital thermometers. What I'm going to do is add salt to this bowl. What the salt does is starts to melt the ice, and that actually consumes heat. This is called an endothermic reaction, and it absorbs heat, which makes the ice colder. And as you can see, this bowl of ice still sitting at around 0 degrees Celsius, but this bowl, -8 and falling. Wow. So there you have it, making something even colder than ice would normally make it. That is a way to make a refreshing glass of lemonade. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
With our new heater and lighter materials, our hot air balloon was floating free. That is, until it tipped over. When that happens, all the hot air inside escapes. But Michaela and I have a solution. So we decided to build an even bigger hot air balloon and add a way to keep it upright. So the process, aside from that, is pretty much the same. We put the end over top of our industrial heater, and I will plug it in.
Get that hairdryer again for good measure.
It's working, it's inflating, but we gotta keep fluffing it up, otherwise it just sort of sags. But you can see the top of the balloon is definitely working. It's a lot bigger than the last one, though. Do you think we made it too big, Michaela?
It's really big. I think it's working.
It's definitely working. Uh-oh, pull your side.
Oh, man.
Oh, it's totally working! I'm so surprised that this works so well. So the stick is gonna keep it balanced so the bottom faces down, but Michaela's gonna tie a string to the stick so that when it goes up, we can keep it centered. Okay, this looks good. You wanna let it go?
Yeah, are we ready?
Okay.
Okay, 3, 2, 1.
Whoa!
Yeah! So let's recap. The hotter air inside the balloon is less dense than the colder air on the outside. And because we were able to get the air hot enough and the balloon light enough, it floats.
Science Max, experiments at large.
Hot air balloon.
Thank you, Michaela.
Awesome.
That was
so cool.
Wait a minute, who has the string?
Oh no!
Oh no, oh no, oh no! Dart suit. No way.
Behold my giant balloon!
Yeah, it's called absolute zero. Please, let go.
By the end of that, my hand is so cold. Wait, I can do this. I can do this.
Science!
Free!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing. Ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh,
we'll
via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay.
Oh, hey, we're here.
It's okay, it's okay. Don't worry about it.
No, I think definitely.
It's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery.
Yes.
More voltage and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century. But no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we were not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet, and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, let me turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. And if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So now let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay.
Work together.
Yep.
Wow.
So that's passed all of our tests.
Yeah.
This is really strong.
Is there a way to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry. Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end? Not really, no. But would you be impressed if I was to balance this coin on top of this coin? Possibly. Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this. And now, I say, a magic word. A magic word! Ha 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 ha! And now, you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing! Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you!
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
we need to keep you safe because you're going to be using these electromagnets to get across this massive beam above us.
That's right. I'm going to stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
My goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets. Woo! You want to go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Oh, okay. Careful. Don't mess it up, Overwhelmo.
Overwhelmo.
Send in the next applicant for the Wizard Academy.
Overwhelmo.
And now, I say the magic word.
Overwhelmo.
I say the magic word. The magic word!
Well, that certainly does seem like magic, yep.
As I balance not 1 coin, not 2 coins. That's a 3.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today's episode is about friction.
How can I hang on to this rope without falling?
Can we reduce it so we can slide around? I'm going towards the wall! Can we increase it so I can climb a wall?
Ha ha! I did it!
Can I use it to fly? Yup! Friction! Today on Science Max Experiments at Large.
Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like to use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle, and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're going to see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Oh, that's got it.
Oh no, this isn't the Science Center. Did I go back in time again?
Oh. It is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in case?
No, it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on, let's go. Russell's waiting.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. A little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Friction, come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset.
Uh-oh. The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil.
How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
Air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got the
Okay, so we put the balloon on the... hold on. Larger balloon!
Oh, okay.
Sorry.
That's okay.
Okay. Uh-oh, twist it so it doesn't...
He's losing his air.
Okay.
All right. On you get. You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go.
It doesn't
feel way too much
It doesn't
friction
feel
on
like
it.
it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon. Something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
A leaf blower.
Right?
High fiving.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs when we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, I kind of prefer my carbon where it is. Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then, Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower-powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at this.
That's amazing.
It's good, right?
Oh, yeah, I love the tube. You know, high volume of air through that.
Yeah.
So yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is a leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air.
I can't control it!
Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me.
I'm going towards the wall! It's like human air hockey! Okay. It's a bit unstable. Do you want to turn it off?
Wow, that worked amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom? Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
And then we could build 2 of them, and we would have 2 discs and 2 ways of moving them.
Are we gonna race?
And we can race!
Yes.
Yeah! Okay,
Yeah.
race. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena.
Hey.
This is amazing.
Thanks, I made it myself.
Wow.
Ready to climb it?
Absolutely. Here we go.
Way to go.
Huh? Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right, and the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We'd probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right.
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my drink. Here we go. Ooh.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro?
Wow.
Right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready.
All right, here we go. Ha-ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have 2 hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got 2 low-friction hover discs, and I'm gonna use the low-friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high-friction rubber ball stick.
Start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Let's go! Let's go! Let's go! Let's go! Go ahead! He's way back! Forward! He's way back! In for the win! It's the winner!
Jay crosses the
Yes!
And then we have our winner. Yes! Over the finish line. It feels way back over there. I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder. Definitely. Wait! I have an idea. Wait, hold. I need your help. Come on. I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Unfortunately, we can't hear what Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. So how important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work.
Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helena and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines.
And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh no! I'm out! Yeah! High five! Yeah! High five! Yeah! Yeah, wait.
Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? The larger fire extinguishers?
I think so.
Okay. See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, we can get like a rack of extinguishers.
Science Max is a show where we take small experiments and do them big.
If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Carbon is an atom that is the basic building block of all life as we know it. You, me, hit myself in the head with the friction sign. That's more of an impact, not friction, really. How can you destroy my life anymore? Set, huh?
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max!
What good is science if you can't use it to give you super strength? Well, I try to do just that on this episode of Science Max. Lifting more, rolling more, and a whole lot of running. Simple machines, today on Science Max Experiments at Large. Greetings, Science Maximites. I have a question for you. Have you ever wanted superpowers? Like super strength? Well, today on Science Max Experiments at Large, I'm gonna give you and myself super strength using the power of science. But we're gonna do things a little differently today. You see, well, the portal hasn't been working perfectly since I built it. But I ordered a new particle impulse controller, and all I have to do is get it back to the lab. Perfect timing. It looks like the portal is broken. Okay, well, no problem. Okay, I'm here. Wow.
That's perfect. One particle impulse controller for you.
All right, thanks very much. Appreciate it.
Enjoy.
Thank you. Well, my very own particle impulse controller, okay. That's as heavy as I thought it was gonna be. All right, Science Maximites, this episode of Science Max Experiments at Large is gonna be a little different because today I'm not gonna have an expert come and help me because I'm gonna move that giant, heavy particle impulse controller all the way across the parking lot and all the way up that loading ramp by myself with nobody's help. How am I gonna move a giant, heavy machine all that way if I can barely even budget? Well, I'm gonna give myself superpowers, super strength with the power of simple machines. And the first machine we're gonna start with is the lever, which I guess I should go back to the lab to tell you about. All right, Sal, I'll see you next time. Oh, hey, how you doing? Let me guess, you got some work to do and you need it done easy, right? I mean, look at this book. I mean, you could pick it up, but what, are you gonna be some sort of book picker-upper person now? Is that all you're gonna do? Is that gonna be your life, just picking up books left, right, and center? No, you're smarter than that. You know what you need? A lever, like this. Now, I know what you're thinking. I know you're thinking, hey, this is just a plank. You're right. That's because you're smart. A plank can be a lever. All you need is two sides and a place for it to pivot. A fulcrum. It can be anything. Look at this. Bam! Now it's pivoting. I put the book on this side, and then I push down on that side. I'm doing work easy. Hey, look at me doing this work over here. If I want to do more work, I could move the fulcrum a little bit further over. Now I do lots of work, but I lift the book a lot further. Look at that. Whoa! Wow! Whoa! Yeah! Huh? What do you say? What do you say, huh? Huh? You don't like this lever? Don't worry. Hold on. I got another one for you here.
Hey, take this stick. All you need is 2 ends and a place for it to pivot. Like this. Bam. Now, it's a lever. This side goes down, that side goes up. Down, up. It's a lever. It's a lever. You want to make a catapult? Use a spoon. The place where the spoon pivots is the fulcrum. And now, it's a lever. It's a lever. It's a lever. Look at this lamp. Now, it's a lever. Scissors, 2 levers. Your forearm, it's a lever, 2 ends, and the fulcrum where it pivots, yeah, the fulcrum can be at one end. Crazy. This fish, you guessed it, now it's a lever. And now you know your levers. Okay, where were we? Oh yeah, levers. So you can use levers to become much stronger, or at least lift something you couldn't normally lift. Levers are simple machines and they work like this.